Thank you very much. Thank you for the invitation. It's a great pleasure to speak in the seminar. So everything that I'll say today will be based on joint work with Dmitrii Zakharov, currently a PhD student at MIT, also here today. To begin, I'd like to tell you a little bit of what and give some motivation. So the problem concerns the following function. If I give you two parameters and little n, one can ask about the smallest integer, positive integer n, such that in every configuration of in d-dimensional space in general position, there exist little n points in convex position. So this is a classical function. It's quite to compute even for small parameters. So first case where it has some content, little n equals 4, in which case this function equals 5, which means that among every 5, we always have 4 points in convex position, and 5 is the smallest number that achieves this. So place 4 points that are not in convex position in the plane. That is easy enough that I can perhaps right here. And so this is a proof that this number is. And to prove that the number is at most 5, one can also draw some pictures, but perhaps the cleanest argument is to recall that the complete graph on 5 vertices is not planar. This is a proof that this is you place 5 points in the plane and you draw the straight segments between them. This is a drawing of the complete graph. And well, not planarity means that two of the segments must intersect. The endpoints must be in convex position. Okay, a bit more generally, so maybe in general, in d dimensions, it's always enough to consider d plus 3 point. Always have d plus 2 in convex position. This is true for every d. And more chance you're seeing this function for the first time. It should not be a priori clear that this number should exist in the first place. In other words, given any choice of little n, why should there be, why should you take sufficiently many points in the dimensional space, then you always have n points in convex position. But of course, it's true. This was established by Erdős-Szekeres in 35. An important paper from Erdős in some sense, also Erdős' first paper. It's a paper where Erdős and Szekeres connect this geometric function with a more combinatorial function. Nowadays, and perhaps at the time, it started getting called as the diagonal Ramsey number for d plus 2 uniform hypergraphs with parameters n and d plus 3. And I want to emphasize that this d plus 3 is the same as this d plus 3 here. I want to remind you the argument. So this number is indeed finite from Ramsey's theorem.
Sorry, can I ask, in 2 dimensions, general 3 of them are collinear, and in higher dimensions?
In 2 dimensions, as you said, and just r to the d, I would d plus 1 points to lie in the same affine hyperplane. Just to avoid so that we don't consider collinear points or points that cluster in a low convex position for trivial reasons. So I was saying this is an important relation because at the time it also kind of an invitation maybe to study alongside with the developments in arithmetic, Schur's theorem, van der Waals, and so on. This was really the motivation to study these things, bounds for them. Let me mention a few things. So first observation, what's a lower bound for this in the plane, at least? So to see that we can construct a set of many points, namely root 2 to the power points in the plane, such that it's n-gone at all. So what's really the picture? It's really starts with 4 points in position, and then the trick is to pick a generic direction, a short vector. I don't know, let's make like, and double the construction in that choice maybe of direction. Let me do it. If you do this correctly, you'll see, okay, you get this with 8 points, and now there are no 6. A convex hexagon, and you keep a generic direction, and you double the configuration, and well, you'll see that you get 16 points, and now no 8. And this process has this feature of the largest convex offset increases by at most 2. And doubles. So this leads to this lower bound. On the other hand, Ramsey numbers, understanding them one problem, and we don't yet understand the Ramsey number for D equals. It's understood well enough to the upper bound from the original upper bound of Erdős and Szekeres. So some bounds for a Ramsey function for 4 uniform hypergraphs. So these are recent, much more recent. So this is doubly the function and then squared. And this is a function that grows faster than an exponential function. So it's something like this. This is log Fox Zakharov. It's by Mubai and Suk. But okay, so these are fairly recent. At the time, Erdős felt that maybe this Ramsey upper bound for the Erdős-Szekeres function is not a very good quantitative one. So in the same paper, they addressed this question and came up with a better estimate from above for this function. So it proved also the following: that this Erdős-Szekeres function of plane is also upper bound by another Ramsey function with somewhat more geometric flavor. This function, I'll write it with 2 parameters. Important for later too. This function is the smallest number n that in every configuration of n points in the plane in general position. I will stop writing general position. Everything will be in general position unless I say otherwise in this talk, in the relevant space. So every configuration of this many points contains at least one of the following 2 structures. So either a convex set of size A that looks like this, which we'll call an A cup, or a convex set of size B that looks like this, which we'll call a B cap. So more formally, what are these objects? An A cup is a set in convex position where if you order the points from left to right after the x coordinate, the slopes of the consecutive segments are increasing from left to right. Or equivalently, any line you drop passing through 2 points, the picture is all above. Same here, the slopes are decreasing from left to right, and that's a B cap. So given this definition, here doesn't really have any content. Of course, many points in the plane, you find either an n cup or an n cap, set of endpoints in convex position, but perhaps turns out it's so not only we have good estimates, we have a precise equality for this. But it rarely happens in Ramsey theory, like extremal combinatorics. And one of the very few examples. So upper bound 2 times n minus 4 choose n minus 2, the central binomial coefficient, which is roughly the n over root n, ignoring constants. So I should say maybe about this line and this function, because this here really lies at the heart of maybe for this Erdős-Szekeres problem, both in the plane and in higher dimensions. So more generally, here's an equality like this. Parameters A and B. So it's equal with following binomial coefficient A plus B minus 4, choosing minus 1 outside. And where is this from? So what's really the main idea? The main idea is in this picture. If I give you these 2 objects that endpoints. So I give you an A cup. This is the A cup picture from before, but now this endpoint here is also cup. Slopes increase all the way from left to right here, and then they start decreasing, starting with here. Of course, there's some happening in the middle there at this. On how the inequality goes, if the slope is 1 more, you can extend the cup, or like in this picture, if the slopes don't continue to increase, they drop. Notice that we can extend the B cap by 1. So gives you an equal or plus 1 cap. In a few lines, it leads to a nice recursive inequality symmetric function in the spirit of recursive inequality we learned for Ramsey numbers. That's also due to from the same paper. This maybe it's at most the sum of the lower complexity functions, where each coordinate and you subtract the minus 1 from here. And this actually holds equality also. It's possible to match it with the construction. Okay, so this story here on this board has a name, which is called cap lemma. And in some sense, beyond the obvious question of maybe doing better than the sport with the upper bound, but some smaller questions on it. First of all, well, okay, we have this plus 1 with equality here for this function. Can you just remove the plus 1 upper bound of this central binomial coefficient just for this function? And this took some time to figure out. It is indeed possible. I'll see that. Also notice that it's loaded with a better construction here. So Another trivial observation is that if I give you a convex set of size n in the plane, then, well, one of the halves is a cup or a cap. Also, part of at least n over 2 points or a bottom over 2 points. So this function is lower bound. And if you have equality, well, this is of the order of 2 to the n divided by that. Again, ignoring constants. Okay, so as I was saying, the start was trying to maybe remove this. This was achieved, and by Chung and Graham in the started the sequence of improvements for this function. Sequence which culminated with a very nice paper by Erdős-Szekeres, 2016, that narrowed down the base of the exponent for this Erdős-Szekeres function. So to prove that this function is n plus some sublinear little of n in the exponent. So we have this man. You always have endpoints in convex position. This little of n was explicit in this paper. It was a polynomial, just n to the 2/3. It wasn't properly optimized. Not long after, a group of people, Olsen, Mojarad, Pak, and Tardo, optimized this and slightly proving that little o of n by root n times some log. With a constant, of course. Okay, so I'd like to tell you briefly what is the main idea behind the Suk argument. Nice, short and sweet. The main idea is to use the following structure result. This is a theorem with Pohoata and Walter, building on previous work of Barani and Walter. This is the following. I'll give you a positive integer k, at least 3, let's say, and set x the plane, large in terms of k, exponentially large. All right, so exponential and then k, but you should not take it too seriously. What the in the back of your head, maybe think 4 to the k first. And then, okay, what can you say if you have a very large set? Well, you have convex k-gons as soon as this number is at least 4 to the k by standard averaging, sampling. You can actually find many convex k-gons. This in terms of, you can say even a bit more. There's a structure you can extract from. There exist k sets, xk, large, so of size, positive set the points. They're in convex position. Here. Any set you pick in the list, its convex hull does not intersect at all with the convex hull of the union. I'll draw a picture for this. Okay, so you pretend that this is 4 to the k for the moment, and find a convex k-gon. That looks like this. Okay. Now we have And what this theorem is saying is that, okay, this multiple convex Huygens cluster, and if you draw the supporting triangles, if I may say so, for this, so you extend the sides, draw this picture like this, then it's possible to prove that there will be some convex Huygens in your list that that has this feature at each of these triangles, a positive fraction of the points. So each such triangle x divided by 2 to the 40. Okay, so these will be the class 3. This is a picture. If you pick section, there is also in convex position. So this is what the picture looks like, and with this thing in mind, the proof goes the following. So if you start with a set X of size roughly 2 to the n, and you want to prove points in convex position, well, we cannot do it lemma, but as we saw here, endpoints. Well, cap lemma is good at cups and caps of size n over 2. Of side n. Okay, so if we choose this k here at the beginning to be some polynomial function at n, this is still close to the end. And now you can find a size n over 2 in each of these triangles. So you can perhaps hope to merge them together. There you find two consecutive, where maybe a cap of size n over 2 looks like this, like cup or a cap of size n over 2 looks like this, and then maybe you can merge them. Their union is a convex set of size n. Two caps that stare at each other through one of the vertices of the supporting polygon. Well, okay, maybe this, in which case, okay, maybe you find Shire caps. They just stare at the floor rather than at each other here. Then, well, you can maybe hope to merge multiple together. Of course, this doesn't rough sketch, but I think with this the proof. Okay, so let me now move on to this is essentially the story in the plane.
Sorry, can I ask, how do you use this structural lemma to, so that's what Suk used to get his result, right? How does he connect?
Yeah, so you apply you start with 2 the endpoints, you apply the structure lemma, you have of size close to the end, lemma in each cluster. Now, cap lemma says you have cups and caps of size n over 2 in each. And now, from some simple combinatorics, you say, well, you either have cups and caps of size n over 2 that stare at each other through a vertex, and you can merge them, or they don't stare at each other, so they tend away, and then you two of the pieces that there are some lies here and there, and you cannot get away with just merging, but it's really roughly the idea. Any other question? Okay. So in higher dimensions, the quantitative on shaky grounds, because, well, this random way gets, of course, worse and worse. The corresponding pieces, as you see, this depends linearly on the dimension. Bounds, I won't even write them for the Ramsey now. They're not completely well understood, but again, it's understood enough that this tower type in N, where the number of grows linearly with the dimension. So this is a very worse and worse. Idea is cup-cap lemma. So while this cup-cap lemma really does a great job in the plane, it's not so clear how to use it in higher dimensions. An immediate bound for this. This on several occasions, and a lot of results generalizing cap. So I'll just mention names. Elias and Matusek of various interesting journals, starting with the abstract version of this, and I think book and also all sorts of generalizations, semi-algebraic kind of world, and then Moshkovitz and Shapira, and others. So many interesting works generalizing cap lemma, but they didn't really apply to problem. However, there's a very silly argument that defies this high uniformity aspect of the problem. So it turns out if you regard this function as a function in the dimension, it's a decreasing function. So the bound applies to all dimensions. As many points are enough in any Euclidean space in R to the D to find endpoints in convex position. The proof is almost trivial, so just doodle something. No, let's say you begin with this many points in R3 that you need in the plane to find endpoints in. And then what do you do? Well, you pick a generic plane. Let's say you project everything. Look at the projections. Of this many projections in the plane, you can find endpoints in convex. Look at the pre-images, they must be also in convex position in space. So argument applies for every choice of dimension there. Okay. How what is happening could even higher dimension. So in particular, could the dimensional Erdős-Szekeres function be much smaller? Than the planar? Should it be easy endpoints in convex position in space to find them in the plane? Multiple predictions. Well, the years. So let me maybe quickly. I'll start with the most entertaining one. The answer is just no. Maybe two-dimensional phenomenon, that's the most interesting one, and somehow in space, say what happens if the points cluster around the. Also, it's more of a prediction in the fact that, well, this trivial chain of inequalities has really been the best known upper bound. So up to projecting from infinity, projecting from up. separating, things like that, up to small modifications, additive things. Exclamation.
So the n is much bigger than the d.
Yes, yes, the dimension is fixed throughout, and we're only thinking about gross. Okay, the second option, I guess, is yes, but okay, perhaps not dramatically smaller. So, so still exponential.
You represent the same person who makes all these predictions.
No,
It would be wrong.
we definitely. So I'll say a few things about that. We definitely oscillated, I think, between them ourselves. So this one, I can make something more precise. So conjecture that this function grows like 2 to the by d plus some sublinear term. So just generalizing, in some sense, the state of the art for d equals 2. If I made the if I'm bolder, suggested the bolder may be between these functions of the conjecture by Erdős and Szekeres on the plane. So we have this complete for all choices of n and d function at n, the Erdős-Szekeres function at n minus a 3. So in particular, this would function is 2 to the n minus 2 plus, which is of Erdős and Szekeres from the original paper. That is also backed up by a construction. The third one, keep this one. Okay, not this one. It's a bit unfortunate to go there, but okay. So third prediction, and maybe dramatically, perhaps ESD of n is sub exponent. Here, ready-made, more precise. Conjecture that this grows the following function 2 to the power n raised to 1 over d minus with the constant in front that depends on the dimension. So this is still 2 when d equals 2. But much smaller function than the ones before. And the reasoning, this is based on the best known constraints available for this problem.
This is the lower boundary.
Yes, this is the lower bound. But okay, maybe this is extremal combinatorics to conjecture that the best now are could be sharp. It might not. This may not be a grounds because this construction is in some sense just a generalization of this doubling construction that I sketched earlier, which already in the plane doesn't seem like the right thing to do. So finally, I can see. Like I said, we were by these stories and for quite a bit working on this. The end. So with Dmitrii, I managed to show that the third prediction is the closest to reality. Easier to find convex sets in plane. So this function is sub-exponential would be equals 3. Just from this inequalities.
We get an improvement with these.
So I'll say something about it in a moment. The short answer is we hope so. So we are currently just in a 3 space. There's a hope. So maybe go right here. Hope. There's a hope that the strategy, at least in principle, generalizes to establish the following relation between any choice, between any two consecutive Erdős-Szekeres functions in the sense of dimension. So we hope to get the following. This is at most Erdős-Szekeres function.
Didn't make it.
Sorry?
Not disprove it stated.
No.
Careful. They were careful only to deal with 2. You said that in the original paper they conjectured E as 2M.
Yes, they conjectured this.
They didn't give something for higher D.
No, they didn't. They didn't. They had the Ramsey bound, and I think later projection argument somewhere, but not the prediction for this. Yeah, somehow this prediction, because it actually is not just a naive generalization of this, it actually holds for a non-trivial range of parameters. So there is a non-trivial function in the dimension for which all the n smaller than that actually satisfy this with equality. So it's somewhat curious that we can check that with element arguments, and then okay, what do you do after? It's just impossible. There were these. Okay, so in general, we hope the following to be true. We hope that this is a more Erdős-Szekeres function in d-1 dimensions, evaluated at some maybe raised with some brutal constant here that depends on. So this would start with this result in d equals 3 and would tell you that there is an improvement. I'm happy to say about this towards the end if there's time. For now, let me sketch the main ideas. Result. So, can I please? Three main ideas. First idea is the cup cap. We can prove that turns out to be useful in this Erdős-Szekeres function. Let me try to state it. So, in the interest of saving some space on this board, here. Okay. What's the setup? I give you start with the polytope in R3. It has no assumptions. It can be unbounded. So some intersection of half spaces might be unbounded, and set X. Three in general position. We say two things. So X is P3 if for every the line passing through them, take the polytope P. And say that X is a P cap, point in X not belong to the convex hole, union P minus X. So what does this look like? Let me draw here some polytope. I think P3 is imagined, so set of points kind of like this. Any line I draw there really hit this. Okay. So again, I can promise the P will look the same. P cap, something that looks so it's a set that when you take the convex hole of it with the the resulting thing might not be in convex position. There could be some points here in the polytope, but if it fails to be, not really because of this. And here is separated from the rest. So
X does not belong to the convex.
not belong. Yes, sorry. So let me side of the board. So proposition, if the P3 set is large, strictly greater than the binomial coefficient raised to the number of edges, one-dimensional of the polytope. Means or some convex set that we don't really know how it's nonetheless of size B. In the interest of time, maybe I won't too much about the proof. It's not a difficult thing to prove. As you may guess, coefficient is the same as the binomial coefficient cap lemma. So we must do some, not just one, consider in several, one for each edge, a posted structure, that one for each edge of the polytope on any kind of set X in R3. Using P3ness, one can find a large to all those posets. Kind of use cap lemma, roughly speaking. I'll tell you on the other hand, maybe what's the thing. So
This proposition is for any fixed point.
yes, for any fixed P unbounded, really ridiculously few edges also. That's important for our.
Can you say briefly something stupid how this generalized as what should I take P to be? Original coupling?
Yes, a point. So just infinity.
Single point.
Yes. Yes. So let me make some sense. I'll read the end game. Be a bit more useful proof. So the end, we want to find some special polytopes to apply this kind of lemma to. So a list of polytopes, P1, PP with constant number of edges. And large sets, subsets of my set X. Say polynomially large. Satisfying two conditions. First condition, each set Zi in the list is Pi free with respect to its own polytope. And two, up diagonally, Zi is contained in Ej, every I different than J. Okay.
Sorry, before you raise this, does this generalize the one that you just raised?
Yes. So short answer is yes, but and there the second value will be a structure result that is appropriate, but it won't be direct generalization of this. But so there are several extensions of this that are relevant for this problem. One is relevant for this bound, and you need a certain robust generalization for something like this. Okay, so why would such a structure be useful? So the point is that, well, okay, if I start with a set X in R3 and doesn't have convex subsets of size n, and is larger than a certain binomial coefficient, let's say X is bigger than this thing raised to some power, let's say C, and prime, I use this C here, C prime satisfies, I don't know, C bigger than the maximum number of edges. Oops. Well, then I can apply cap lemma in R3 to all these Zi's, and it's large enough. So if this happens, then Zi prime inside Z such that Zi prime Zi cap size at least n over t. The other possibility not happening because this has no convex subset of size n. For all I, but then this right, because Z1 union ZP prime would be is also convex. Each of these pieces have size n over t, size n, right? So because the picture kind of looks like this. I have here Zi prime, some nice cap. Is all of them. So this piece of size n over t is convex, and it behaves nicely when you glue. And this picture is symmetric with respect to all the blocks. So the union must be one. So then quality holds in reverse. And if one is take t to grow with n, this is sub-exponential. So that's kind of the point. Cap lemma. The structure is what we use. This concerns the main part. This is the following. Maybe I should do this picture. This is quite convenient. So start with some k. And I get x in general position, large in terms of k. Right anymore. So I'll put here some dependence on k. Then take clusters, all large, so the size of x with a constant. So if that two things are first thing, so if you just pretend that this is the same condition as it was in the whole Walter result in the plane, so x at least something like to the 40 times k. Here's one consequence. You can find k clusters such that, well, there's some plane below, where if you project, you have that structure in that plane. Right? So the projections are in convex position. Some projection map. Okay. It's not very interesting. We need a second condition, that's specific for R3, certain separation condition. This condition for every partition, okay, for every partition of the sets, okay, maybe for every partition of the interval from 1 up to k, so the set of indices, 4 intervals, and have the following separation between the sets. So I'll draw some partition. So let's say I1 and I3 here, I2, I4. Doesn't matter what kind of intervals, open, close, semi-open. Whenever you have a picture like this, it comes with the following separation. If you take the convex whole of the sets coming from the intervals above, it's separated by some plane whole of the sets coming from the indices below. So yeah, I won't be able to say anything, I think, about the proof, except that several things from convex geometry, heavy type argument, applications of half sandwich theorem. So first one is that applies the result for a choice of parameter in the spirit of just assuring the first condition. And then, well, it's easy to, so using ham sandwich repeatedly, one establishes a separation condition, a local separation condition on 4 tuples of sets. And then the arguments to boost that kind of condition to a global separation condition. Just with convex geometry, one also has to use Ramsey's theorem to create this boost. But that's kind of the idea. I'll end with the third, and giving you a sense of how these things fit together. So let me something in here. How to make use of this separation condition. It's an application of so Ramsey's theorem again will produce this desired structure. So the setup, and we call set, and there's no convex subset of size n. Okay, we apply the structure theorem. The result x1 up to xk, x the clusters from there. Now, rather for every 3 indices in this list, one up. Well, from 1 up to k, define the partition of the interval for intervals. So one has conditions depending how one defines. And then those different separation conditions. So possible splittings here. Gives you 2 sparsity. So 2 polytopes that each contain a fair amount of the same. So 2 polytopes minus PG plus such that with this of 3 half spaces, there are 2 things. Like I said, xi is in PJ for a ton of the indices. So in 2 of these intervals, something like this. Is contained in PJ plus other 2. So just the first condition. Take a look at the way I wrote the intervals. It doesn't say it's really not in any polytope. Condition is about that set for every 2 points in xj2, the line xy intersects at most 1 polytope from the 2. So I'll draw a picture. I think it's more important. The set xj2. And this condition is saying that we have these quite substantial polytope the other sets. So 2 of the sets are in here, the other half are in. So this is PJ minus, this is PJ plus, and we have a picture like for every triple. Okay, so this can tells you essentially there is a structure on xj2. Opposite structure, another point, x belongs to the convex hull, Pj minus union y. So here, something like this. I take the convex hull of PJ minus X is inside. This relation, it's easy to check that it satisfies all the conditions. It's a poset. Notice in this poset are pretty interesting. If you take here, the line passing through every 2 points in the chain hits. If it hits all the time, then it never hits PJ because of this condition. So a chain corresponds to PJ plus free set. And well, the line through corresponds to something that's PJ minus free. And Dilworth's theorem tells us that, well, we can define a proper two coloring of K choose 3. So we can add if it has PJ plus free set of size root xj2, or color it blue, PJ minus free set of size root. So this is a well-defined coloring. Apply Ramsey's theorem, find a monochromatic clique. And this is exactly, if you unwind this, this is exactly this, this structure here. A monochromatic clique will have to be doubly logarithmic. So this is a 3 uniform Ramsey number application. K's or K grows with then this T, the size of the monochromatic clique from Ramsey. The T will also grow. So Ramsey gives you this. Completes. I'm running out of time, so I won't torture you with more details. So I'll end here.
Questions for Cosmin?
So what is the quantitative little of n in 3D that you get?
It's a great question. So I think I have some room here. So the argument, as I sketched it, and as it's done in our preprint, gives a little o term that is n over 5 times iterated log. This can be always come from these different applications of Ramsey's theorem primarily, also from this iterated application of sandwich theorem and the proof of here. But that thing, one log there can be removed using Woodcott's polynomial partitioning ideas. So this can be optimized to 3 logs. We know. It doesn't really give you anything, but polynomial saves, and we're somewhere. We don't know what's the right question. There could be some polynomial exponent, but I think it wouldn't be terribly surprising. Getting closer to little O than the sharp actually for 3D, but I think we're not emotionally ready for that conjecture.
Okay, I have 3 questions, but the first question is just whether I can ask 2 questions. Do you hear me?
Yes, yes.
Okay, so first of all, what do you think is the right bound?
What?
What do you think is?
Oh yeah, yes. Earlier, we don't really know. I think maybe nowadays
Make a bold guess.
plus epsilon chance that little O is close. Little O n, so something close. Not so polynomial in n.
But you think that a little O of n? Okay, I mean, will it be close in all dimensions, or you think you will be going to something?
Yeah. So I guess big hinging on what happened. Yes, there should be an improvement in higher dimensions. If the 3D close to this, then probably it's like this in all dimensions. I would get by some logs, but not.
Okay.
I wouldn't expect some phase transition or something. But who knows?
The third question, which was the second question, the questions I wanted to ask. Is so what kind of polytopes? Can you describe what polytopes you get? Is it
Yeah, so as I was saying, they're very, very, so they're unbounded. They're
no, combinatorially.
oh, combinatorially. Yeah, I mean, so these polytopes obtained by separating these here. So for each triple, you write separating things.
Yeah, it sounds a little like they would be kind of close to cyclic polytopes, but they're not cyclic polytopes, right?
No, I don't think so. No, I don't see any reason why. This is really the only kind of combination I can think of.
So if suppose I were an alien who doesn't really know what R3, but for some reason I do know Helly's theorem and all the common statements you can make about points and convectors. How many of these arguments, what percentage of this can, like in the spirit of the original Ramsey proof, where you can local features and then it gives you things you can, how much of it do I genuinely need to work with R3 as R3 rather than those conditions hold?
Okay, so I think that interpret your question. So one way is that, so these Ramsey numbers everywhere. So this most explicit one I wrote down. So there's an application here. So we apply Ramsey uniformity 4 to put our hand on the structural condition. Both of these applications are really purely combinatorial Ramsey. So they have extra properties, the colorings. Maybe hope to exploit, we have some improved bounds. But that's still, I guess, I don't think there's a improved bounds without being a original Ramsey. Yeah, there is, so as the second interpretation, there's a hope to remove Ramsey arguments completely, but we don't really know yet how. If that would be possible, it's very likely then the answer is not really little o, and maybe it would be a power saving there. But we don't. I don't know on percentages.
Okay, is it sort of more meant taking what you already have and then just trying to sort of phrase it entirely in this very austere language where the only things I'm allowed to know are which points are in the convex hull or which other points?
And when every argument can be phrased like that.
Is that true? Is that another thing? That,
Yeah.
And the like, so R3 is characterized by Helly's theorem in R3 or something.
I mean, we use some Pythagorean stuff. This only R3 input is like the structural result and use a bunch of Pythagorean, like some pattern lemmas in principle and raise stuff.
Yeah. I think there may be different takes on this that we can try to formalize.
Does the Erdős-Szekeres problem make sense beyond the RB geometry? I don't know, RB hyperbolic space or something. Maybe that's
yeah, so I think short answer, there are several, I think, more, so there are abstract versions of Erdős-Szekeres out there. I don't know any hyperbolic, but there are these notions of abstract convexity along with the line, so you can say what a convex hull means, so set theoretically in some sense. Questions in that setup, and it's been studied. Many nice results. They tend to not have good bounds without, but yeah, I don't know. Maybe in a more geometric alternative setup.
There's also pseudo-line stuff.
There's pseudo-lines, yes. So one of the things I mentioned was generalized, so the optimization of super result in the plane, and so it also came with the generalization where the straight lines, only condition is that every two such things meet in at most one point, can define convex hulls and convexity. In that kind of regime, you have the same bound there actually, not so that's what Holmes and Mongerat, Bach, and Erdős did. But That's literature about this. Like, there's something more relevant.
Okay, let's thank Cosmin again.